Welcome. For a parallel RLC circuit, this video derives the underdamped natural response voltage across all three components due to an initial condition inductor current I sub L naught.
Notice how the 300 milliamps marked in the schematic matches the starting point of the magenta inductor current transient signal.
The circuit variable is voltage. The characteristic roots are expressed in terms of R, L, and C. The initial conditions of the voltage and the derivative of voltage at time 0 are used to calculate the constants in the solution equation, resulting in this damped sinusoidal voltage, equation 14.165b.
Most of the content in this video is based on Chapter 14 in this book, called First and Second for short. The equation numbers in this video, starting with 14, are the exact equation numbers from the book for your reference.
To start the parallel RLC natural response detailed derivation process, let's write Kirchhoff's current law, KCL, in equation 14.12b for the bottom node of the circuit. I sub L0 is the initial condition inductor current. It is a single static value. All three currents in the KCL equation are functions of time. Next, let's bring in the branch relationships for the inductor, capacitor, and resistor. Specifically, we have the equations for current through each component as a function of voltage across the component.
The initial condition inductor current from the schematic can be seen in equation 14.13b.
Substitute each of the branch relationship equations into the KCL equation, replacing the current terms in the KCL equation 14.12b, resulting in the KCL Integro differential equation 1. Rearrange the terms in equation 1 to put the capacitor term first, as shown in equation 14.15b. Differentiate the whole equation 14.15b to obtain equation 14.17b. Multiply equation 14.17b by the inductance L to obtain equation 14.18b. Equation 14.18b is the equation we need to solve to derive the natural response voltage of the parallel RLC circuit. The circuit is responding to the initial condition inductor current I sub L0.
Okay, but I don't see the initial condition inductor current in equation 14.18b.
Good point. I sub L0 is not in equation 14.18b. The initial condition inductor current will reappear when we use initial conditions to solve for constants. The differential equation 14.18b contains the voltage, the derivative of the voltage, and the second derivative of the voltage. Now, how do we solve equation 14.18b? The derivative of the exponential function, shown in equation 14.22, includes the exponential function itself. Therefore, the exponential function in equation 14.20 makes a good educated guess for a possible solution to the differential equation 14.18b. The complex frequency S, shown in equation 14.21, is made up of sigma, the real part, and j omega, where omega is the imaginary part. We'll try using the exponential function from equation 14.20 and equation 2 above in our solution process. Substitute the voltage exponential function, equation 2, into the RLC differential equation 14.18b, resulting in equation 14.23b. Perform the differentiations in equation 14.23b to obtain equation 14.24b. Factor out the exponential term ke to the st from each of the three terms in equation 14.24b, resulting in equation 14.25b. We know that equation 14.25b equals 0. This means that either the exponential term ke to the st or the term in brackets must be equal to 0. The exponential function cannot equal 0 for finite values of time t. Therefore, the term in brackets must equal 0, which we express in equation 14.26b as the characteristic equation. Solving the characteristic equation 14.26b for S, the complex frequency, will give us part of the information needed for the overall solution voltage.
The other part will be the constants k.
To solve equation 14.26b for S, apply the quadratic formula in equation 14.28 to equation 14.26b to obtain equation 14.42a for the roots S1 and S2. Equation 14.42a shows the characteristic roots. S1 corresponds to the positive version of the plus or minus sign. S2 is minus. The blue dotted arrows show how the roots from equation 14.42a get inserted into the proposed voltage solution general form equation 14.5b, which applies to all the damping response cases. Equation 14.60b gives the criteria for the underdamped response case. When equation 14.60 is true, the quantity under the square root sign in equation 14.42a is negative, resulting in complex conjugate roots indicative of the decaying oscillatory natural response behavior. Next, we're going to manipulate equation 14.42a into a form better suited for our solution function. First, let's make the complex nature explicit. Underneath the square root sign in equation 14.42a, introduce a minus 1 squared term to obtain equation 14.62b. Of course, minus 1 squared equals 1, so no overall change was made. But now we can take part of that -1 squared term outside of the radical sign. From equation 14.62b, a -1 term comes outside of the square root sign as the square root of -1 in equation 14.63b. The other -1 term from the -1 squared term remains under the square root sign where it distributes and terms change sign. Finally, from equation 14.63b, we replace the square root of -1 with the complex operator j in equation 14.64b. We know that our roots are complex. For convenience, let's introduce a frequency term called omega d, shown in equation 14.65b, which is the imaginary quantity from our roots equation 14.64b. When we plug our roots into the voltage solution equation 14.5b, using sigma and omega d notation, we get the complex exponents in equation 14.68b. Rearrange the exponents slightly to make the overall exponents negative in equation 14.69b.
We're halfway there. We now know all the information we need for the exponents in terms of our circuit parameters R, L, and C.
Now we just need to solve for the constants K. To solve for the constants K1 and K2 for equation 14.69b, we will use the initial conditions of the circuit variable, the voltage, and the initial conditions for the derivative v prime of t of the circuit variable. At time 0, the exponent terms in equation 14.69b go to 0. E to the 0 equals 1, so the e terms go to 1, giving us equation 14.145b and 14.146b.
Now we have our first equation for finding K1 and K2. We'll need another equation and we'll solve the equations simultaneously.
For calculating the initial conditions on v prime, the derivative of the voltage function, we first need to differentiate the voltage solution equation 14.69b to generate the derivative equation v prime of t in equation 14.147b. Then evaluate v prime of t equation 14.147b at time t equals 0. The exponents of e all go to 0, making the exponential terms reduce to 1, as shown in equation 14.148b.
Next, we need to evaluate the left side of equation 14.148b and express it in terms of quantities that we know.
For some help and insight evaluating the left side of equation 14.148b, let's look at the branch relationships for a capacitor, shown here in equation 14.149b, where the current through the capacitor is expressed as the derivative of voltage across a capacitor, which is what we have in our parallel RLC circuit. Better yet, we know that the capacitor instantaneous current at time 0 will exactly equal negative the initial condition inductor current, which is something we know.
How do we know this for certain?
There is no other place the instantaneous inductor initial condition current can go at time zero. It can't appear through the resistor because instantaneous resistor current at time zero would mean an instantaneous voltage across the capacitor and the other two components. An instantaneous finite voltage change across a capacitor implies an infinite current through the capacitor. Rearrange equation 14.149b to isolate the derivative as shown in equation 3. Knowing that all the initial condition instantaneous inductor current flows into the capacitor, equation 3 leads to equation 14.150b for the derivative of the capacitor current evaluated at time zero. Now we have the derivative of the voltage evaluated at time zero expressed in terms of circuit quantities that we know. By the way, the red current arrows in the schematic are only valid instantaneously at time zero. Checking this capacitor current evaluation with Q-Spice simulation, we can see, at time zero, the negative capacitor current of the same 300 milliamp magnitude as the initial condition inductor current. Notice the use of UIC in the Q-Spice transient command. Equation 14.150b expresses the derivative of voltage evaluated at time zero in terms of the initial condition inductor current and the capacitance, quantities that we know. We used the C subscript in the specific context of the capacitor branch relationship, V sub C of t, on the left side of equation 14.150b. In the general context of the parallel RLC circuit, the capacitor voltage is the only voltage, so we don't use a subscript. Equation 14.150b gets simplified in equation 4. The I naught over C term from the right side of equation 4 then replaces the V prime naught term on the left side of equation 14.148b, as shown in equation 14.152b.
Now we have a second equation, 14.148b, which we can use for solving simultaneously with equation 14.146b for the constants k1 and k2.
Equation 14.153b gives us k1 in terms of k2. Substitute minus k2 into equation 14.148b and distribute the minus sign to obtain 14.154b, which no longer contains a k1 term. Equation 14.154b can now be solved for k2 in terms of given circuit parameters. Gather k2 terms in equation 14.154b to obtain equation 14.156b. Solve equation 14.156b for k2, shown in equation 14.158b. And finally, We have one simple substitution step to solve for K1 in equation 14.159b. Now that we have expressions for K1 and K2, we substitute them into equation 14.160b, the voltage solution equation for the parallel RLC circuit. The result is equation 14.161b.
This voltage solution 14.161b in exponential terms is fine, but I would like to see v of t as a single trigonometric function that I can more easily plot.
Good idea. Let's start by gathering the exponential terms. That is, factor out the common I sub 0 terms in equation 14.161b to obtain equation 14.162b. Next, we partition the exponential terms in equation 14.162b to factor out e to the minus sigma t, which is the decaying exponential part, resulting in equation 14.163b. The exponential equation 5 is utilized in this step, and it applies to complex numbers. We also separated a 2j term from the denominator and grouped it with the exponential terms in equation 14.163b. This allows us to apply the trigonometric exponential identity in equation 14.164. The result is equation 14.165b, the final solution for the natural response voltage of the parallel RLC circuit due to inductor initial condition current.
Thank you for watching and learning with us.